Hi, I'm Benjamin Tran, and this is going to be a video about parallel algorithms and their applications in modern computing. If you ever wondered how a website can serve millions of users at the same time, how a self-driving car processes sensor data in real time, or how a large language model gets trained on more text than any one person could read in 100 lifetimes, the answer, in large part, comes down to parallel algorithms. Today, I'm going to walk you through this topic in 4 parts. First, we'll cover why parallel algorithms matter and the core theoretical tools we use to learn about them. Things like work, span, and Amdahl's law. Second, we'll look at the major programming models, shared memory, distributed memory, and GPU computing, and how each one matches a different kind of hardware. Third, we'll go through design techniques that let us actually build parallel algorithms like decomposition, divide and conquer, and the scan primitive. And finally, we'll ground all of that theory in 3 real application areas: graph processing, distributed deep learning, and geometric clustering. By the end, my hope is that you'll walk away with a mental framework for looking at any large computational problem and asking, how could all of this be parallelized, and what would it actually cost me? So why do we need parallel algorithms in the first place? For decades, computing performance improved mostly because clock speeds kept increasing. The same program that just ran faster on next year's chip. That trend basically stalled in the mid-2000s because of power and heat constraints. Since then, performance gains have come from adding more cores, more threads, and more specialized hardware like GPUs, rather than making a single core faster. At the same time, the problems we want to solve have gotten much larger. Think about training a neural network on billions of parameters, or analyzing a graph with billions of edges, like a web graph or a social network. A single processor working sequentially just cannot get through that kind of workload in a reasonable amount of time. Parallel algorithms are how we take advantage of all those extra cores, GPU threads, or entire clusters of machines by splitting a big computational problem into smaller pieces that can be worked on at the same time. That is really the core motivation for this whole topic. Modern hardware is parallel, modern datasets are massive, and so our algorithms have to be designed with parallelism in mind from the start, not just tacked on afterwards. Before we get into specific algorithms, I want to define a few terms that show up constantly in this field, because they can be easy to mix up. Parallelism means multiple computations are physically happening at the same instant, on different processors or cores. Concurrency is related, but a distinct idea. It means multiple tasks are in progress and making forward progress over time or some time window. But they might be interleaved on a single core rather than truly simultaneous. Every parallel program is concurrent, but not every concurrent program is parallel. Next, 2 of the most important analytical tools in this field are work and span. Work is the total amount of computation across all the tasks. Basically what a single sequential processor would have to do to finish everything. Span, sometimes called depth, is the length of the longest chain of dependent operations. The critical path that can't be shortened no matter how many processors you throw at the problem. From these 2 numbers, you get speed up, which is how much faster the parallel version runs compared to the best sequential version, and efficiency, which tells you how well you're actually using your processors rather than wasting them on overhead. And scalability describes whether your algorithm keeps performing well as you add more and more processors, or whether it hits a wall. Keep work and span in mind, because they come back constantly when we evaluate whether a parallel algorithm is actually good. This brings us to a famous result called Amdahl's law. which explains something that surprises a lot of people the first time they see it. Adding more processors does not give you unlimited speedup. Amdahl's law says that if a fraction of your program simply cannot be parallelized, some sequential bottleneck like a setup step or a shared resource, then that sequential portion puts a hard ceiling or hard cap on your maximum possible speedup, no matter how many processors you add. For example, if 10% of your program has to run sequentially, your theoretical speedup can never exceed 10 times, even with an infinite number of processors. This is a humbling but essential idea for algorithm design, because it tells you where to focus your effort. The sequential bottlenecks are usually the real target, not just throwing more hardware at the problem. Textbooks like Pacheco and Malensek, An Introduction to Parallel Programming, walk through this in detail. And it's one of the first things anyone learns when they start working with MPI, pthreads, or OpenMP, because it shapes how you think about where parallelization actually pays off. Now that we have the theory, let's talk about how parallel programs are actually built. There are a few major programming models, and each one matches a different kind of hardware. Shared memory programming assumes all your processors or cores can see the same memory space directly, which makes communication cheap, but requires careful synchronization. Distributed memory programming assumes each processor has its own private memory, and processors have to explicitly send messages to each other to share data. This is how large computing clusters work. GPU-based programming takes a different approach entirely, using thousands of lightweight threads that all execute the same instructions on different pieces of data. And increasingly, systems combine all of these into heterogeneous computing, where a program might use multiple machines, each with multiple CPU cores, each of those paired with a GPU. Shared memory programming is usually what people learn first, because it maps naturally onto the multi-core laptop or desktop most of us are using probably right now. Two of the most common tools here are pthreads, short for POSIX threads, which give you fine-grained, low-level control over creating and managing threads, and OpenMP, which lets you parallelize loops and sections of code using simple compiler directives without managing threads by hand. The trade-off with shared memory is that because every thread can touch the same data, you have to be careful about race conditions. Situations where two threads modify the same variable at the same time and get an inconsistent result. That's why synchronization tools like locks, mutexes, and atomic operations are such a central part of this model. It's powerful and relatively easy to get started with, but it only scales as far as a single machine's memory and core count will take you. When a problem is too big for a single machine, you move to a distributed memory programming. And the dominant standard here is MPI, the message passing interface. In this model, every process has its own private memory. And if one process needs data that lives somewhere else, it has to send an explicit message and the other process has to explicitly receive it. This is exactly how supercomputers and large compute clusters solve massive scientific and data processing problems. You might have thousands of nodes, each running its own copy of the program, coordinating through message passing. The upside is that this model scales to enormous problem sizes, essentially as far as your budget for hardware allows. The downside is that communication over a network is much slower than accessing shared memory. So a huge part of designing a good MPI program is minimizing how much data you have to move between nodes, and overlapping communication with computation wherever you can. The third major model is GPU programming, And this is where a lot of the recent excitement in machine learning comes from. A GPU is built completely differently than a CPU. Instead of a handful of powerful cores, it has thousands of much simpler cores, all designed to execute the same instruction on different pieces of data simultaneously. That structure is a perfect match for problems like matrix multiplication, image processing, and neural network training, where you're applying the same operation across huge arrays of numbers. Kirk, and Hajj's textbook, Programming Massively Parallel Processors, goes deep into this architecture and into CUDA, which is the programming model most commonly used to write GPU code. The catch is that GPU programming requires you to think differently about memory. You have to explicitly manage data movement between the CPU's memory and the GPU's memory, and organize your threads into blocks and grids to get good performance. And in practice, most large-scale systems today are heterogeneous. They combine CPUs for control logic and I/O, GPUs for the heavy numerical lifting, and sometimes multiple network machines on top of that, tying together everything we've just talked about. Now let's talk about how you actually design a parallel algorithm, independent of which programming model you're using. The first step is usually decomposition, breaking a big problem into smaller, ideally independent pieces. Task decomposition splits the work itself into distinct operations that can run in parallel, while data decomposition splits a large dataset into chunks and applies the same operation to each chunk. Divide and conquer is a natural fit for parallelism, because when you recursively split a problem in half, each half can be solved independently and in parallel, and merged back together at the end. It's the same idea behind parallel merge sort or parallel matrix multiplication. One particularly important building block is the scan or prefix sum operation. Guy Belloch's classic 1989 paper showed that scan operations can be treated as cheap, unit-time primitives in a parallel setting, and that a huge number of algorithms, things like radix sort, quicksort, and even minimum spanning tree algorithms, can be rebuilt around this one operation to run efficiently in parallel. Beyond decomposition, good parallel algorithm design also means paying attention to load balancing, so that no single processor is stuck doing much more work than the others, and minimizing synchronization and communication overhead, because every single time processors have to wait on each other or exchange data, you lose some of the speed up you worked so hard to get. Now let's move on to applications, starting with graph processing, which is one of the richest areas for parallel algorithms. Think about breadth first search, finding connected components, computing shortest paths, ranking web pages with something like PageRank, or coloring a graph so that no two connected nodes share a color. All of these show up constantly in real systems, from social networks to recommendation engines to network routing. The challenge is that real-world graphs can be massive, billions of vertices and edges, and they don't decompose as cleanly as, say, a matrix does, because the structure is irregular. Some vertices have thousands of connections, and others have just one or two. Dulipala, Belloch, and Shun published an influential paper showing that you can design parallel graph algorithms that are theoretically efficient, meaning that they have probably good work and span bounds, and still be genuinely fast in practice on real hardware, closing a gap that a lot earlier theoretical work hadn't fully addressed. That combination of theoretical guarantees and practical performance is really the gold standard we're aiming for across this whole field. The second major application area is machine learning, and specifically distributed deep learning. Training a modern neural network involves an enormous number of matrix multiplications repeated over millions or billions of data points. And that workload is naturally parallel. But scaling it up to many GPUs or many machines introduces real engineering challenges. Ben Nunn and Hoffler's survey on this topic breaks the problem down really clearly. There's data parallelism, where you split your training data across multiple devices, and each one trains a copy of the model. And then there's model parallelism, where the model itself is too big to fit on one device. So you split the network's layers or parameters across multiple GPUs. Coordinating all of this requires efficient communication patterns, like the all-reduce operation used to average gradients across devices, and it's a huge part of why training the very large models we hear about today is possible at all. Without parallel and distributed computing, the scale of deep learning we see now simply wouldn't exist. The third application area is a bit more geometric: spatial clustering and minimum spanning trees. A Euclidean minimum spanning tree connects a set of points in space using the shortest possible total edge length, and it turns out to be a key building block for hierarchical clustering methods like HDB scan, which are widely used in data analysis to find groups of similar points without having to specify the number of clusters ahead of time. Wang, Yu, Gu, and Shun published fast parallel algorithms for exactly this problem, using a technique called well-separated pair decomposition combined with a parallel version of Kruskal's minimum spanning tree algorithm. What I find interesting about this line of work is that it shows parallel algorithm design isn't just about graphs or matrices. Geometric and spatial problems have their own structure, and exploiting that structure carefully is what makes a truly fast parallel implementation possible, rather than just parallelizing a sequential algorithm in a naive way. Before I wrap up, it's worth being honest about the limitations of parallel algorithms, because it's not exactly a free and easy thing to understand. Communication costs is a big one. Moving data between processors, especially across a network in a distributed system, can easily become the actual bottleneck, even if your computation itself is well parallelized. Synchronization overhead is another challenge. Every time processors have to wait for each other at a barrier or coordinate access to shared data, you lose some of your theoretical speedup. Memory contention can slow things down too. When many threads are competing for the same memory bank or cache line, an uneven workload distribution, where some processors finish early and sit idle while others are still working, can quietly waste a lot of your available parallelism. On top of all of that, designing algorithms that continue to scale well as you add more and more processors is genuinely difficult. An approach that works beautifully on 8 cores might completely fall apart on 8000s. These challenges are exactly why work, span, and Amdahl's law matter so much. They give us a framework for reasoning about where these costs are going to show up before we've written a single line of code. So, to bring this all together, parallel algorithms exist because modern hardware is fundamentally parallel and modern problems are fundamentally large. We looked at the core theory, work, span, and Amdahl's law that lets us reason about how much speedup is actually achievable. We looked at the major programming models, shared memory with pthreads and OpenMP, distributed memory with MPI, and GPU programming for massively data parallel workloads. We looked at design techniques like decomposition, divide and conquer, and the scan primitive. And we looked at 3 concrete application areas where all of this comes together in practice: graph processing, distributed deep learning, and geometric clustering. The common thread across all of it is that getting real speedup out of parallel hardware requires careful algorithm design, not just more processors. As datasets keep growing and hardware keeps getting more parallel rather than just faster, this kind of thinking is only going to become more important. If you want to cycle back to any of the topics, timestamps will be in the description, as well as links or titles of the books and papers I mentioned in this video. Thanks for watching.